Morning, everybody. I found my face. Doing a little bit better today. Symptoms are resolving. Still feel really tired, but did get a good night's sleep last night, which helped a lot. I posted your exam topics, which of course are not showing up right now, because why would they? I just did it. Literally, while you guys were coming in, realized that I had forgotten to put them up. I went heavy on chapter 26. If you look at the list of topics here. So lenses, corrective eyewear, telescopes, right, are all directly out of chapter 26. Mirrors, I think were they 26 or 25? I don't remember. To me, it's all the same topics. They're 25 because it's reflection. History of light I did in class. That one, just know who's who. You're good. And then resolution and thin films we're doing in this chapter right now. But yeah, it is kind of 26 heavy. And I'd apologize for that, but I don't feel bad about it. All right. What was that?
You're apologizing. If you don't feel bad, apologize.
I didn't. I said I'm not. I would apologize, but I'm not. But I don't feel bad about it. Is that not what I said? We can check it on the YouTube later. I don't know. I don't remember what I said.
Run the tape.
Just words. Just words. So we'll see how far we get. We might have to call an audible when we get back from spring break as to the timing of the exam. It'll be those topics, but it just depends on how much I talk about stuff like this. I can't help myself because what we are going to study in this chapter was my graduate work. Like thin film interference is what I am specialized in. So sometimes I just can't help myself. So we'll get there. We'll get there though. This hummingbird, bird plumage in particular, but this is true for insects, particularly butterflies. Certain plants, different sort of optical phenomena in nature. The plumage on this bird, these almost iridescent colors that you see here, are being brought about by a lot of biological structures. There's oil on the feathers, there's spacing of air between the different barbs of the feathers, that sort of stuff. But it all comes back to something called interference. In the case of this bird's wings, it's a constructive interference, but you see those deep blues and blacks and greens and oranges and all that kind of stuff? That's brought to pass by a complex interaction of light waves as they interact with the material of the bird's feathers right there. And these examples keep going and going and going, and I'm going to bring up a lot of them in the course of our discussion today. But what we need to tackle is, number one, how waves work. Number two, Thomas Young, remember him? And his two-slit experiment, how he blew the door open on the fact that light's a wave. And then we're going to use Thomas Young's experiment, which is an experiment. It's not really useful for anything. It just showed that light was a wave, but the practical applications of it aren't that strong. We're going to take the idea of that and move into the practical applications of things like this and other phenomena that I just can't wait to tell you about because it's really good. Okay, so let's talk first of all, a little bit of review from Physics 2A. Don't panic. Wave superposition. So this is really the thing that sets a wave apart from a particle. This concept and idea that a wave can be at the same place at the same time as another wave. Particles, when they try to do that, just reflect off of each other. But waves can combine. So if I take, for example, a wave pulse that's traveling, say, this way, and then I have another wave pulse that's traveling that way, What happens when we add them together? When they cross over each other, what's the result? It's a big bump, isn't it? They add together, right? Both are amplitudes. If this has an amplitude and this has an amplitude, this has twice that amplitude, right? We add them together. And then if you have one that's up and the other one that's down and they're coming towards each other, what happens when we add them together? Then we get zero amplitude, right? So this is referred to as constructive interference. Interference is whenever a wave overlaps with another wave. They're interfering with each other. But the question is, how are they interfering with each other? Well, in the case where their amplitudes are boosting each other, we call it constructive interference. I'll give you one guess as to what the other one's called. Good. I'm not sure if I'm spelling interference right, but I don't care. So we're going to take this phenomenon where waves can be at the same place at the same time and can either add together or destroy each other and apply it to optics, apply it to light, and apply it to the interactions of light with materials. So that's the 2A part, okay, that we had to remember back when we were studying waves. All right, so moving into Thomas Young and his experiment and the double slit. The double slit is an interference phenomenon. And I'll show you a slide here in a second of kind of what the experiment looked like. But we're taking two different waves of light. The two different waves are made from the same source. And from these two sources, we're going to have the waves come together at some point in space. If that point in space is a place where the wiggles are opposite each other, we get that destructive interference. But if the 2 points come together such that they are waving, right, in concert with each other, we'll have constructive interference. Now, in terms of light, what do you think constructive interference might look like? Think about two light beams, and they both wiggle up at the same time or wiggle down at the same time. And we shine that on a screen. What would it look like? It would be really bright, okay? Because with light, it's the amplitude in the wave that determines its brightness. And so what would destructive interference look like? It would be dark, right? We're wiping out a beam of light, right? We've got a beam that's coming up, a beam that's coming down. They cancel each other out. That's zero amplitude, and it should look dark. And that's what an interference pattern looks like. It looks like a pattern of alternating bright and dark fringes. We call them fringes, not just dots, because we're fancy that way.
When light passes through two thin slits that are closely spaced and onto a screen, it produces an interference pattern of bright and dark spots. These slides have 3 such pairs of slits, each with a different separation. We'll pass a laser beam through each pair to show the resulting interference patterns. Here is the setup of laser, slits, and screen as seen from above. This is the pattern on the screen from a pair of slits separated by 0.62 millimeters. This is the pattern from a pair of slits separated by 0.26
See how it got bigger and spread out?
Note that the pattern is spread.
I said that.
Here is the pattern from a pair of slits separated by 0.09 millimeters.
Focus on the fact, though, that you get
spread even more.
Thank you, a bright and then a dark, right? A bright and then a dark, a bright and then a dark. That's a telltale pattern. This is a smoking gun for the fact that light is being interfered with, and in the case of the double slit experiment, interfering with itself. Again, I'll set that up for you in a second. But this is what it would look like sort of looking up close at this interference pattern, okay? So a bright fringe, okay, would be a place where we have one of these bars of light, and then a dark fringe, right, would be the spaces in between. Which one is the constructive interference? The bright fringe. Which one's the destructive interference? Dark fringe. We're good, right? Until you see things like this. And you go, what the heck is going on here? So the way Thomas Young set up his experiment is he had those two very closely spaced slits. And he didn't have lasers. Okay, lasers were invented much later. And so he took light and he had to go through a trick of kind of collimating it, getting it all to line up. And it was white light, and so his experiments were a little bit harder to see, and it had to be very dark in order to pull it off. But he was able to get light to shine evenly onto this double slit. So he had these waves of light that were all traveling, and they hit the slits at the same time. And so as they hit those slits, the light would bend through the slits and begin to overlap and interfere with itself. Do I have a better picture? I don't have a better picture of that. So if we take a look at the geometry of this. Now, I don't want to go into the weeds here, and I don't want to show, that's a lie. I do want to show the full derivation, but I'm going to restrain myself and I'm not going to do it. I do want to point out, though, that there's something really, really critical about why this interference happens in the first place. So let's take an arbitrary point on the screen. We're going to pick one that's up, say up here, right? Okay. Now in this last picture over here, we can see that there's like a symmetry above and below. So I'm really not going to talk about what's going on below because it's all the same, okay? But there is a, if there's a bright one up here, it's going to be mirrored down here. Okay, so we have these two slits. They're separated by a distance d, and they're both going to travel to a point on the screen. And they're not showing us do you see how they put the two wavy lines here? Does anybody know what that means? It means there's a lot more of this diagram, but we're cutting it out, okay? Because the slit separation here is usually measured in like tenths of millimeters, like really, really tiny, but then the screens are like meters away. So you need really big distance between screen and slit, but you need really, really close slits together, and so they don't want to draw this thing to scale because we need a screen the size of the building, okay? But as you can see here, we're measuring the angle theta as it comes off these two slits. One of these beams has to travel further than the other. Is it the top or bottom wave or beam? If we're doing a point up here, which of these two has to travel further? The bottom one, right? Because the top one is closer to that point, isn't it? The extra distance, this little delta L here can be found, okay, from the triangle that's formed right there. And that little extra distance called the path length difference. This is an idea that's going to become important for when we do thin films. The path length difference, we're going to set equal to a condition. And I'll mathematically describe these things in a bit, but I want to do the ideas first. Interference takes place because one wave is offset from the other. Now, in that offset, the offset could be zero, meaning that they match. But the offset could also be any other number other than zero. But waves, one of the big features of waves is that they repeat themselves. A sine or cosine function, you get back to exactly the same thing every time you go 2 pi around the unit circle or whatever. And so it should come as no surprise that there will be multiples of offsets that give us exactly the same thing. Let me see if I can't try to help you understand what's going on here. So if I take, let's just take a sine function. Okay, so there's a sine function, right? And I shift this sine function to the right. Okay, I'm just gonna let it evolve and move to the right. Well, it's gonna look something like that, isn't it? Okay, if I shift it a little, and how much have I shifted this function? Now, we can think about this in terms of like pi's, or we can think about it in terms of wavelengths, so we're actually going to do both, okay? But remember, the wavelength of a wave is the peak-to-peak distance, right? How far if the peak shifts over so that it's right here now, how much of the wavelength have I shifted over? Am I making any sense? Good, half, right? Like I've shifted this over half, like I traded a peak for a trough, right? And that's a half wavelength shift, okay? A half wavelength shift gives you what kind of interference? I add this to this, and this to this, that's destructive, isn't it? Okay, do not hard code that one into your brains yet. There's going to be exceptions to these rules. But what I want to do is teach you the language of how we talk about constructive and destructive interference. We'll get to the details in a second. Okay, if I shift it some more, ran out of room, such that like this one gets shifted all the way over, I'm going to be back to that. Okay, so I shifted it another half. What's a half plus a half? A whole. And so now I match with my original. And what kind of interference am I going to have? That's going to be constructive, isn't it? But what if I shifted 3 wavelengths over? What am I going to get? Constructive. If I shift 10 wavelengths, if I shift any integer number of wavelengths, I will always get back to constructive interference. So what this means is if 2 waves are offset by a multiple value that is an integer of the wavelength, you're guaranteed to get, in this case, constructive interference. Okay, so what shift do I need for destructive interference? Half integer, okay? And the way that you do half integers is you take your counting number. Now m is a number that goes 1, 2, 3, so on and so forth. It can be 0 in the case of destructive, okay? And if you look over here on the right-hand side of the screen, you can see that they are labeling the different orders, the different repetitions of this pattern. See how we have brights and darks and brights and darks? M equals 0 corresponds to what we call the central bright fringe. Okay, it's the center of the pattern. Anytime you get integer values, just n, of the wavelengths, then you're on a bright spot for 2-slit interference. M being a counting number, 1, 2, 3, 4, 5, right? Okay. What happens when m equals 1 and we're doing a dark fringe? What do we get? Get 1.5, right? What about 2? 2.5. See how it's always a half, right? That's language for we're going to get a dark fringe. So the conditions, the right-hand side of this equation that I'm setting up for you, okay, is either going to be m lambda or m plus a half lambda. And for 2-slit interference, m lambda is constructive, and for and the m plus a half is destructive. Okay, those are the 2 broad. You can have conditions in between, but we're not going to cover those. Don't worry about those. Okay, we're just going to do the extremes of constructive and destructive. All right. The left-hand side, this path length difference. Waves are coming out of 2 slits, and they're traveling and meeting a same point on a screen. We want to set the condition for that point. We either want it to be constructive or destructive, bright or dark. But we have to acknowledge that the bottom wave went a further distance. That extra further distance that the bottom wave goes turns out to be equal to d sine theta. Just trust me on that one. It's sitting right there in that triangle if you really want to look at it for a long time. Okay? But that delta L, the path length difference that they got on that screen, is the extra amount that the bottom wave is having to travel. If we set the extra amount the bottom wave has to travel to a full integer distance, we will get constructive interference. It would be like shifting the wave one complete wavelength. But if the path length difference is equal to a half wavelength shift, we're going to get destructive. So what we end up with are two equations for two-slit interference. It's always d sine theta. The path length difference is d sine theta. But it's either going to be equal to m lambda for a bright fringe or n plus a half lambda for a dark fringe. I don't want you to get too caught up in where this came from or why. What I want you to take away from this is that there was a difference in how far the waves were traveling. And that difference, the extra distance one wave travels versus the other, can be set so that we can get constructive or destructive interference. That's the idea that I need you to carry forward into what we're going to do with thin films. Right? But before I do that, I'll do an example of working with a two-slit interference. Two-slit interference is historically very, very important because of what Thomas Young did in proving that light was a wave. It's the experiment we always go back to that's like, this is what started the revolution, right? Okay, this was our Declaration of Independence. This is light, right? Light's a wave, it's got wave-like properties. This interference pattern doesn't exist without this formulation that Thomas Young came up with. But I actually want to talk about thin films because they're more interesting. This picture is trying to help you see, right, how these integer and half integer counting numbers work, right? There's always this central zero-width dot, okay? Bright fringe that we reference everything from. It's the fringe where the two slits, the light rays, okay, are coming exactly the same distance. And since it's exactly the same above and below, there's no path length difference between them, it's always going to be a bright fringe. And then we start counting, right, halves and integers on either side. Again, it's mirrored on either side. But if a problem says you're on the third bright fringe, well, there's a zero with one, right? And you count 1, 2, 3 upwards, and you know where you are. So let me do an example, okay, of working with two-slit interference, just to help you through that. I gave you one homework assignment because Thomas Young deserves at least one homework assignment for the work. Is that how I'm supposed to decide what homework? All right. So wavelength is involved here. You can see that, so we need to know the wavelength of the light that we're passing through. We will always use monochromatic light. It's a really fancy word for one color. So we're not going to do white light. We'll always be like a laser that's shining for us. That's kind of a greenish color right there, 546. And it forms an interference pattern. So they told us that the screen is 8.75 meters away, right? So what have they given us? So there's my slits. This is not going to be to scale. Here's my screen. Remember, the slits are always a distance d apart. And then the screen is, I usually use the capital L for the distance to the screen. And then they're giving us some weird words here. If the distance on the screen from the central fringe to the first bright fringe is 5.1, okay, so there's a center line for our m equals 0 condition. And what is going to be at m equals 0 always? Bright, a bright fringe, right? So I'll do bright fringes as my red dots here, okay? So each one of these is a bright fringe, okay? You know what, let me space those out just a little bit more. So it's a little bit clearer for you guys. And of course, they're down here. I usually don't draw those, okay? So we're going from, if the distance on the screen from the central fringe, which is the m equals 0, to the first bright. So first bright, what m value is first bright? 1. If this distance on the screen is 0.0516, what did I just do there? I converted the distance into meters, didn't I? Want to be careful that I do this, right? Okay, get all the same unit. Because if I start mixing centimeters with meters with nanometers, it's just going to be a bad day. Okay, so these are all in meters now. Okay, then they want us to find the slit separation D. This is what they're after right there. Okay, so in two-slit interference, we can either be talking about a bright fringe or a dark fringe. What are we talking about in this problem? A bright fringe, right? So our equation that we're going to use, path length difference equals condition, is going to be d sine theta equals m lambda. And how do I know how to choose m lambda? Because I'm on a bright fringe. Okay. We know lambda, don't we? They gave us the lambda. We know m. M is equal to 1. We're looking for d. What the heck is sine theta? Well, there's like where are the angles in here, Mr. Balogh, right? We tend to think of the angle as just kind of being like right here, and that it's almost the same for both of those slits, okay? But there is a trick, and I don't think your book does this trick, which is really sad because it is a really useful trick. So I'm going to teach you this really useful trick, okay? And you're going to see me use it in 3 different places in this chapter, okay? Get your calculators out. It can be your phone, it can be your calculator, it doesn't matter. It's just that you need to be able to put your calculator into radians mode. Yeah, gross, right? You never know how to sit back and we'll be stuck forever. Okay? Alright. So, what I want you to do is I want you to take the sine. Where's my. There's Brett. I want you to take the sine of 1 radian. Again, you're not 1 degree, but 1 radian. And tell me what you get. 0.8. Blah, 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 blah. Okay? Right? And you're like, well, that's not interesting. You're right, that's not very interesting. Now take the sine of 0.1 radians.
It's not really interesting.
0.99833 blah, 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 blah. Oh. It just got a little more interesting. Now take the sine of 0.01 radians. How many 9s are there? 4. And then an 8. And then no, you don't see it? It's one of the greatest features of the sine function ever. No, still don't see it? As the angle gets smaller, what does the value approach? Well, yeah, 0. I'll give you that one. Sine of 0 is 0. But look, how close is 0.01 to 0.00999998?
Really close.
They're the same, aren't they? Like, for all intents and purposes, that's the same to any amount of significant digits. Sine of 0.1 is pretty much equal to what?
0.1.
0.1. This one, not so much, right? 1 and 0.8, even for a physicist, are like, well, that's not quite, right? This is called the small angle approximation. For small values of sine, and for those of you that want to talk in degrees, okay? For any degree less than 5 degrees, the value, the radian value of the sine, that angle, is equal to the value that the sine puts out. In other words, the value of the function is equal to the angle. That means that sine theta is very much equal to theta itself. Sine of theta. Okay? They're approximately equal to each other. And there's another trig function that follows the same pattern that involves sine. It's just not spelled sine because you divide it by cosine. Tangent. For small angles, and we have very small angles here. The distance between bright fringes is 5 centimeters, and the distance from the slits to the screen is 8.75 meters. This room is about 10 meters long, right? And then we're talking about something that's about half the height of this wall strip. Like, what's the angle from that wall over to here? Really small, right? So, I don't need to use sine. I can use tangent, or I can just use the angle. They're all going to give me the same answer. Now, your book just leaves it as sine thing and lets you deal with really small numbers in your calculator, which is fine. But what is the tangent of that triangle right there? What's tangent? Opposite over adjacent. And tangent is equal to y over L, which is equal to sine theta, which is equal to theta, isn't it? So that means I can write, instead of sine theta, I can write dy over L. And I can just skip this whole angle business altogether. It's really handy, and I don't know, I mean, I kind of understand why your author didn't do it. But it's just so useful, because you can go, I mean, can you put the y and the L and the sine of the thing and find the height? Sure, you can do all of that. But why do all of that? We just got y over L and it's done. Anyway, so I'm solving for D. It's going to be m lambda L over y, which is going to be 1 times 546 times 10 to the minus nanometer. 9. 6 was a good guess. Times L, 8.75, all over 0.0516. And I put in numbers, and I don't even know if I have this. I do. 92.587 times 10 to the minus 6 meters. Or 93 microns. So how close do those slits need to be? About, what is that, 5.5 human hairs? Close to each other, right? Okay. Like really, really close, right? Again, don't worry about the small angle approximation. I taught that to you because it's a really neat trick and I'm going to use it again. You literally can think of sine theta as y over L in all of these problems, right? So dy over L equals m lambda for constructive. If we were doing destructive, it would be dy over L equals m plus a half, right? Okay, so you can just, when you see me write dy over L equals a condition, what I'm doing here is I'm just getting angles signed. Because trig functions are done. They just are. We don't understand them, we can find them in our calculator, but we can liken them directly to physical things in the problem, it's much better. All right. That's all I want to really say for Young's double slit. Really, really important experiment in physics, but when it comes to the practical applications of the interference of light, oh, I forgot something. Not on purpose. Got my box of goodies again. Remember these? Right? Okay. So,
Those are your glasses.
okay. All right. I don't know if you can see it from where you're sitting. Okay. But do you see the reflection in my glasses? What color is it? Can you see the color shift? Is it white or is it like purple red?
Oh.
You see a greenish to purplish red? Yeah, okay. Maybe this one. This one's a little bit easier to see. You guys see that from over there? Okay. Okay. That's an anti-reflective coating. One of the things I noticed when I first started teaching as a grad student, I begged my way into being able to teach lecture classes. Most graduate students wanted to just grade papers. I was like, no, let me teach. Don't make me grade, let me teach. I went in, I started lecturing, and I mean, I know I'm not handsome by any stretch of the imagination, but students wouldn't look at me. And I didn't even have dad jokes back then. I was like one of them, right? But they didn't like, they would look somewhere else, right? And I'm trying to like maintain eye contact, communication, all that kind of stuff. And they're just like, it's like this, right? And I finally, one day I just kind of had it. I was like, guys, is it my jokes? Are it my genes? What's going on here? And they're like, what are you talking about, Mr. Bailey? You're great. I was like, but you won't look at me. And they were all shocked. They were like, of course we look at you. Who else are we going to look at? You're the only guy in the front of the room. And I was like, but whenever I try to maintain eye contact, you look away. And they're like, no, we don't. I was like, yes, we do. And finally, one student put his hand up and he said, Mr. Balogh, we can't see your eyes. I was like, oh. And he's like, no. Come sit where I'm sitting, put your glasses on the desk, come sit where I'm sitting. And I put my glasses down, I walked out, and sure enough, the only thing I could see in my glasses was the reflection of the fluorescent light. Okay? So what was going on is I was basically like wearing sunglasses the whole time. Only it was the reflection of the lights, right? And I notice this the next time you're either talking with somebody who's wearing sunglasses, or you have sunglasses on and somebody's talking with you. They really won't look at you. Why are they looking at you? They can't see your eyes. And we clue in on eyes, right, when we're communicating. And so when the eyes are blocked, our attention will be listening still, or we'll be looking at your nose or something, but we're not like staring into your soul, right? And so the next time I got glasses, I graduate paycheck, right, okay? I actually ponied up saved my pennies. I was like, can I get the extra expensive anti-reflective coating on my glasses? And they're like, sure. You know, poor graduate students usually don't ask for it, but okay. And I noticed an instant change in my students paying attention to me. I'm not the center of anything, but like the communication just felt better because they could see my eyes. So what does this have to do with anything? We're going to talk about that anti-reflective coating. But before we get there, we need to talk about something even more important. Bubbles. Bubbles are the best. I mean, the only thing to take second place to a bubble is a balloon, right? But there's something about floating round things that just are amazing. And you blow them and they float all over the place, right? But even more than that, look at this thing. It's a spherical rainbow. And this has everything to do with my glasses and people being able to see my eyes and hummingbird wings and anti-counterfeiting technology and dollars. Does anybody have a $20 bill? I'm asking the wrong crowd. Anybody have a $20 bill? Okay, I would like everybody to know I'm taking $20 from Eliana. There has been no promise of grades or anything. Right, okay? And it will come back to them and there will be no magic tricks, okay? So, standard American $20 bill. You'd be hard pressed to find an older one now, okay? All of them are almost new because of the anti-counterfeiting stuff that they put, and this one has it. Okay, so there's lots of different things in this bill that are anti-counterfeiting, but one of them is the $20 symbol, the number is down here in the corner. Okay? I don't know if you've ever noticed, but you can take a $20 bill. I don't think you guys, maybe you guys can see it from where you're sitting. Does the color of that 20 down here in the corner change? People in the front can be able to see it. Those of you, the next time you have a $20 bill, which would be when you get a real job or something, right? Okay? Right? It's kind of hard, right? Did everybody know that I gave it back? Everybody saw that, right? Okay? So you can just twist it right there and affirm for me that it's changing color. Thin film interference on a $20 bill. The inks that are being used in that number right there are calibrated to cause that specific shift in color and frequency, and it has everything to do with bubbles and hummingbird wings and anti-reflective coatings. This is what happens when you put oil on water. I mean, I'm not a fan on oil on water because it usually means something has broken somewhere, right? But man, it's pretty. I mean, just look at the kinds of pretty rainbows there. Mesmerizing patterns. What is going on? How is all of this? I could stare at this for forever. It's so cool. So cool. Here's that anti-reflection. See that purplish cast right there? To get the anti-reflection. Okay, so let me show you. This is what real optical physicists do all day long. We just play with bubbles.
Soap bubbles display dazzling colors when seen under bright
They're so
light.
great!
If we dip this cylinder into a soap solution, a thin flat
Takes a
film is
scientist
placed
to
on
make
the
it
mouth of
sterile,
the
right?
cylinder.
Yeah.
We'll shine the light off the soap film and onto the screen to show how the colors we see depend on the thickness of the film. Immediately after the film
So
is
cool!
produced, the colors are pale and difficult to see. As the fluid drains to the bottom, the film thins at the top and the colors become more distinct.
It's getting brighter and brighter and brighter. Where are they coming from? It's like magic. What kind of just interference is happening at the top? Destructives turn black up there, right?
Now the film is so thin at the top that the colors have disappeared, leaving a dark space where almost no light reflects.
I already explained that. You're late. Look at how vibrant they are. And then time passes.
Finally, the film breaks.
And sadness ensues. That's okay, I have more.
When two transparent plates are pressed together and viewed in a bright light, interference patterns can often be seen. We'll use this monochromatic sodium light and two large glass plates to demonstrate one type of pattern. With just one glass plate in place, the reflection of the sodium light is uniform. When we add the second plate, an interference pattern appears. The pattern shifts as the flexible pieces of glass relax into position.
See the dark fringes? See the bright fringes?
Squeezing down on the plates causes a shift in the pattern.
Old phone protective screens used to do this. Okay, the old cell phone screens, even without the protective cover, used to do this, right? And the reason it would happen is because a thin layer of air had been trapped between two pieces of glass or plastic, and it was causing that interference pattern to happen. Normally under like white light, it's hard to tell, but if you ever got like a single color light or something like that, it would stand out, and people would be like, "Oh, my phone's broken." Okay, so what's going on here? All kinds of stuff. First of all, thin film interference comes about because waves change their phase when they bounce. I just said a big sentence, what did it mean? Phase, the phase relationship between waves, I've already taught you, okay? A wave that matches another wave, or in other words, is an integer wavelength shift from each other, are said to be in phase. Waves that exactly mismatch each other are said to be out of phase. You can have different phase relationships, but the two main ones are an in phase or out of phase relationship. In the language of trig functions, this bottom one right here, this half-shifted one, has been shifted pi radians, okay? And what is pi equal to in degrees on the unit circle? 180. So we will refer to a 180-degree phase change or a 180-degree phase shift as a complete reversal of a wave in its orientation. In other words, it's flipped over. When light interacts with a surface and the light is traveling from a low index to a higher index material, it will undergo this reversal. We talked about this a little bit in 2A when we were talking about waves on strings. If the wave pulse coming down had a fixed end, it would invert itself as it came back. This is the optical equivalent of that. So when light travels from lower index to higher index, the bounce, the reflected ray, will shift its phase. The refracted ray, which is not drawn here, will not shift itself. It's only the reflected one that shifts itself. This is a very important piece to understand if we're going to untangle and you're going to survive thin film interference. Lower to higher, phase shift. And it's a complete 180 degrees. It's a reversal, okay? N plus a half. If the light is traveling in an index that's higher than what it's trying to get into, then there will be no phase change. Notice, I have not assigned constructive and destructive now. I'm just saying that the wave itself will change its phase based on the material properties. So what are the rules? What happens if it goes from higher to lower? No change. But if it goes from lower to higher, phase change, one complete, like a half, it's completely out of phase. Okay, from its original. The picture that we are going to use all the time is this one. This is the visualization for every thin film interference phenomenon. So this is what's going on. Light. And I know it's not drawn this way. I'm going to draw it the true way, and then you're going to see that that's not useful, and then we're going to draw it the fake way. We are always going to shine light directly down on a surface when we're talking about thin film interference. Okay? So it comes down, hits the surface. A thin film is sitting on a surface. So it's like a surface material, and then there's a film of something else. So this has got like some index, the film has some index, and then there's a material on top, usually air. Okay? What will the angle of refraction be for normal incidence for 0 degrees? Going way back to Snell's law. If we hit just perfectly straight down on the surface, does it refract at all? No, there's no refraction. So we will get a bounce off the surface. The law of reflection states angle in equals angle out. So 0 degrees in, 0 degrees out. One of the beam splits in two. That's a lie, but it's good enough. Okay? And one part of it bounces up while the other part continues into the film, where it bounces off the bottom interface and comes up. It also continues on through. But do you see the problem with this diagram? Yeah. I can't tell the difference between a reflected ray, a refracted ray, the one coming off the top, the one coming off the bottom. It's a mess. But because we only do normal interference, normal angles for you guys, okay? I had to do all the angles in between, okay? This picture doesn't work. It just fails us in helping us understanding what's going on. So we come over here to the screen, okay? And we've got, this is our ray coming in. Now, does light come in at angles for you guys? No, okay? We're just using an angle here to make the drawing clearer, okay? So it comes in and we get a reflection because there's a change in material. But we also get refraction. So the light comes down, and again, because there's another interface, I'm going to get a reflection. that then comes back out, and then I'm gonna get another transmission. When we draw this in our problem solving, this is how I usually do it. I will draw two lines that represent the film, right? So I've got my film right here. Technical term for the bottom part is the substrate. It's what the film is sitting on. And then you have your incident material, which is on top. Okay? This is how I will draw it. I will just draw a ray coming in, bouncing off the top, ignore refraction, and then just draw another one bouncing off the bottom. Again, we're doing this for clarity and organization. We're not trying to exactly replicate what's going on. Notice I did not draw the refractions. I didn't draw anything going into the substrate because the only two rays that matter are the ray that bounced off the top layer of the film and the ray that bounced off the bottom layer of the film. They're the only two we care about when it comes to this interference pattern that I'm going to use to describe bubbles and everything else. The index of refraction determines everything. And it's relative, like what's happening with the incident material and the film, what's happening with the film and the substrate. We got to follow the rules. So let's pretend that the incident material is air, the film is, oil, and it has 1.1, and the substrate is water with 1.3. Those are all the indices of refraction, okay? So conceptually, you have to be able to do this. You've got to nail this part of it, because every thin film problem, you must rederive the meaning of the equations I'm going to give you. The equations are going to flip their meanings based on the physical situation that you have, and so we need to be able to walk through this. Okay, so between the air and the oil film, what kind of phase change are we going to have, if at all? We're going from 1 to 1.1. So in that bounce, what's going to happen? There's a 180 degree phase shift, right? So what I like to do is I like to come in and I like to just write 180 on that ray right there. That tells me that it's 180 degrees shifted from the original one that came in. And then on the bottom layer, where the second bounce occurs, we're going from 1.1 to 1.3. So what is that shift going to be? Also 180, and it's 180 from the original ray. Okay. If that phase relationship is maintained, in other words, we don't change anything, they're both 180 on those two outgoing rays. When those rays add together, what kind of interference is going to exist? Good, it's constructive. And why is it constructive? I mean, they're both 180, but that means they're both flipped exactly the same amount and they line up and they match. And so it's going to be constructive interference. Okay, well, why would it change, Mr. Balogh? Well, okay, let's do an example where we go from air to water to oil. Okay, so we get the bounce off the top surface, we get the bounce off the bottom surface. Okay, let's take a look at this. The first bounce going from air to water. Is that a low to high or high to low? We start at 1, we go to 1.3, that's a low to high, so what happens? 180. Okay. Film substrate boundary. That's a high 1.3 to lower 1.1 index change. So how does that one flip? It does not. And so if we maintain that, that's a big if. If we maintain that relationship, what will those two rays do to each other? They will destruct each other. Do you see how those two rays, one of them is at 0 and then another one's 180 degrees different? Those don't match. And so that will be destructive interference. But this is only half the story. Because there's something else happening that we've got to take notice of. And it's this thickness right here. Do you remember how with Young's double slit experiment, it was a path length difference equals condition? How much extra distance does the bottom wave bounce have to go compared to the top? Can you see it? It's not T, because that ray has to go from the top down and bounce back up before it comes back out again. It's 2T. So the path length difference is twice the thickness of the film. That's thickness, it's not time. The path length difference is twice the thickness of the film. And then we are going to set that path length difference equal to conditions that aren't what you think they are. And I'll explain about that in a minute. Except there's more. The wavelength of light changes in the material. This is why the wave speeds up and slows down for different indices of refraction. The index of the wavelength in a material is equal to the wavelength in a vacuum divided by the index of refraction. Putting that all together, our path length difference and our lambdas over here, these are lambda sub n's. They're the wavelengths in the materials, but it becomes cumbersome to have to calculate that all the time. So really we just substitute in, we'll just say m lambda we'll just say lambda over n. Excuse me, because lambda is the wavelength in a vacuum. And then because physicists hate fractions, we will move the index of refraction over. So this, you'll see me write this constantly. I'll say the path length difference is 2nt. Okay? That index of refraction is along for the ride because the wavelength in the film is changing. Path length difference is really twice the thickness of the film, but I also have to account for the fact that the wavelength changed. Technically, does the index of refraction belong on the right-hand side? Sure. But fractions are evil, so we're not going to deal with it. Okay, so how do we apply all of this knowledge, and why are you so excited about Mr. Balogh, and what does this have to do with me? All fair questions. Let's do an example first. I forgot to plug in my laptop, and it's threatening to go to sleep. Okay. So, what is going on here? You've got to start with, don't worry about what they're asking you to do, okay, or asking you to find. Identify the film. What's the thing that's thin here? Thin film interference. This says that there's a very thin layer of material that's sitting between the air and something else, right? It's a sandwich. And that film will exist, right? And be the boundary between whatever's on the outside and whatever's below it, okay? So this is a soap film. They tell us straight out what the index of refraction is. So the index of the film is 1.33. Soap has an index of refraction very close to water because soap films are mostly water films. So what we are actually doing here are bubbles. This is the physics of the bubble and why we're going to get all those pretty colors. Okay, so we know our film consisting of soap has an index of 1.33. Okay, it's in air. So think of a bubble in air, right? What's on the outside of the soap film? Air, it's 1, right? And what's on the inside of the bubble? Trick question, it's magic. But also air. Okay. This is where you just start and you figure out what the phase changes are. Again, notice, I'm not really worried about the rest of the problem yet. I want to nail down what's going on with the rays of light as they strike the surface. So I draw both of them. I'm going from 1 to 1.33 on top. What number do I put on that one? 180, right? It's a low to high shift. Okay, the bottom bounce, high to low. What am I going to put on that one? 0. Okay. Stop there. Don't think constructive or destructive. Just realize that the physics of the bounce has got these two rays out of phase with each other. We have two conditions. It can be path length difference equals a full shift in the wavelength, or path length difference equals a half shift in the wavelength. Those are the two things that could happen. And we could like play with this thickness here, such that the thickness is that half of a wavelength down, half of a wavelength up. That would be a full wavelength shift. Or it could be a quarter down, quarter up, in which case it would be a half wavelength shift. All kinds of things are going on. And take note of this. Be very, very careful about what I'm about to say. The two equations say the same thing all the time. What changes is their meaning. That was crazy, Mr. Bale. How can they say the same thing every time in every problem, but change their meaning? 2nt equals m lambda says, don't change the relationship between those two waves. M lambda means we are not going to shift the second bounce. We're going to keep it at whatever it's doing. The m plus a half version says add plus 180 to the second bounce. That m plus a half is a 180 degree shift. So, the equations always use this. They say exactly the same thing each time. What they say is either don't change the second one or change the second one by 180. And how do you know which one is which? Which is the one that says add 180? It's the one that says half of it. Is everybody with me on that point? It's very important. This never changes, because what I'm about to do is going to confuse you. Okay. What does it mean now for this particular problem? If we don't change that relationship, if it stays 180 and 0, what are we going to have? Destructive interference, right? It's 180 and 0. So that means that for this problem, this is the destructive equation. Now, the m plus a half equation tells us go and add 180 to this second bounce. And if I did that, they're both 180 now. And so what is that going to be? Constructive. The meaning of the equation, the application of the equation is going to shift for every problem. Every problem is different when it comes to figuring out which of these equations is destructive and constructive. What never changes is what they say. M lambda always says, don't add anything to that second one and see what happens. M plus a half says, change the second one by 180 degrees. And then see what happens. So in every problem, you have to determine which of these is the destructive, which of them is the constructive. If you're guessing, you have a 50-50 chance. Some of you are like, I'll take those odds, right? But if you're informed, you have a 100% chance of nailing which of these equations to use. You have to do that every time. Don't try to game this system. Don't try to I guess if you wanted to work out all the possibilities, you could, but it takes longer than just learning this, okay? And then applying it every time. The problem solving, I haven't even looked at the problem to figure out what I need yet, right? I'm more interested in understanding what the heck is going on. Draw a picture. Figure out the phase changes. Figure out what the equations mean in the context of the problem. Once you have that down, once you've identified which equation is for destructive, which equation is for constructive, now we can figure out what the question's asking us. What are they asking me to find? What's the thing of the unknown? Reading comprehension. What is the thickness? Right? What is the thickness? They're asking me to solve for what? T. Okay? They're asking me to solve for T that produces what? Constructive interference. Aha! Which equation am I going to use to solve this problem? One on the right or one on the left?
Right.
One on the right, the m plus a half. And your brain's going, but Mr. Balogh, Young's two-slit thing, m plus a half is each other. I know. This is not Young's two-slit interference, okay? Right? This is thin film. And the leopard changes its spots depending on what environment it's in. So, constructive interference means I'm going to use the constructive condition for this problem, okay, for red light. So they gave me the wavelength, didn't they? So, to solve part A, I'm going to use my constructive equation. 2nt equals m plus a half lambda. I know lambda, it's 652. I know n. What's n going to be? There's 3 indices here. Which one do I pick? The film, right? The 1.33. I know what 2 is. I'm solving for t. Okay, so solve for t. T equals m plus a half lambda over 2n. Okay, great. What's m? What is m allowed to be? Remember? 1, 2, 3, 4, 10, 6,000. It's got to be an integer, right? So which one do I pick? They gave me a clue. What is the minimum thickness? As m gets bigger and bigger and bigger, the thickness is going to get bigger and bigger, isn't it? Just adding in. They want to know the least. So how do I make this as small as possible? What m value do I pick? 0. I'm allowed to pick 0 for this one because they won't give me 0. I mean, the minimum film thickness for any interference is 0, which means it doesn't exist. Okay? So if I choose m equals 0, 0 plus a half times my wavelength, 652 nanometers, all divided by 2 times 1.33. Okay, Mr. Balogh, you didn't do the times 10 to the minus 9. Why didn't I do the times 10 to the minus 9? What are the units of 2? 2. What are the units of index of refraction? No units. What are the units of a half? No units. What's the only unit that's here? Nanometers. So I can leave it as nanometers. Or convert it to whatever I want, right? But why convert it if I don't have to? Okay, so that's 652 over 4 times 1.33. 123. So I can read my writing. So there is the minimum thickness. If I wanted to find the next thickness that would work here, I would put in m equals 1, and I could find the next thickness, and so on and so forth. Okay, that was part A. Which visible wavelengths will destructively interfere? Mr. Bailey needs to pay more attention to his autocorrect. Will destructively interfere when reflected from the, okay, so the part B, I'm now doing destructive interference. So what equation am I going to use? The destructive one. 2nt equals m lambda. All right, so which visible wavelengths, oh my gosh, they're asking me to solve for what? Not just one. They used plural, didn't they? What the heck is going on? So 2nt divided by aha! There could be more than one here, right? Because what is m? 1, 2, 3, 4, 5, right? So on and so forth. So let's see, that's 2 times 1.33 times 6, no, thickness. I found the thickness of the film. It was 123 nanometers, right? All divided by m. That is 326 on top divided by m. Okay, so these are my lambda sub m's. So for lambda 1, I'm going to take 326 nanometers and divide by 1, which is 326, isn't it? Lambda 2, it's 326 nanometers divided by 2, which is 163 nanometers. Lambda 3, 326 all over 3, which is 109. What's happening to each of these wavelengths? It's getting smaller, isn't it? It said which visible wavelengths? What's the visible range? 400 to 700. Do any of those fit in the visible range? If I kept going, am I going to get between 400 and 700? No. So what's the answer? None of them. That light will not destructively interfere. 652 is red light, which means we're going to get a lot of red light bouncing off of this film. We are going to constructively interfere when that thickness is 123 with that light, so we're going to get a lot of red light bouncing out. We're going to get reds, we're going to get blues, we're going to get greens, we're going to get pretty bubbles. All brought to you by Thin Film. Sadly, we have run out of time. And now it's spring break. And so I'm going to have to wait a whole week, 2, longer, I don't know, till next Monday, before I can talk about more things. I got more examples to do of how these equations are going to change themselves. Okay? In the meantime, I want you to have a fantastic spring break, right? I want you to come back to me safe and in one piece, right? Those are your marching orders, besides the homework that you have to do, right? But we will we'll finish this on Monday, the Monday we get back from spring break. Maybe. Depends on how much I talk. If I don't see you tomorrow, be safe and have a good spring break.